Hey, this is the lesson on the volume of a sphere, and the formula for volume of a sphere comes from calculus, okay? But this video kind of helps us get our heads around it. It's kind of cool. So let me just show you it really quick, and we'll just see what this guy has to say about it. Okay, don't worry if you don't completely understand this. Okay, but what he's explaining is how we can think about why the formula is 4/3 pi r cubed. So this idea here, when he zooms in, it's hollow in the inside, but the idea is the volume of that sphere, we could cut out these tiny little pyramids where their base of the pyramid was the surface of the sphere, and all of those together would fill the sphere. Okay, and now he's going to look at the formulas, and this is where the formula we can think about it coming from. So he's saying that each of these individual pyramids, the height of that pyramid would be the radius of the sphere, right? Because they're all coming together at the very center of the sphere. Okay. So, and then we know this formula, 1/3 base area times height. Okay. Because we used it in a previous unit. Okay, so this formula right here, 1/3 base area times height, that is the volume of one of those little pyramids, and that's a formula you should know. Okay, he substitutes it here with radius because remember the height is the same as the radius of the sphere. Okay, and then here he's saying, what if we added together all of those little pyramids, which there would be, I don't know, maybe like 100 of them, I don't know. Okay, what if we added them all together? And we don't know how many there are, so that's why he has this dot 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 right there. So what he did here was he undistributed. Okay, so you know the distributive property, right? If you were to multiply each of these terms in parentheses by the 1/3 and then multiply them by the r, you would get back this expression here. That's the sum of all the volumes of the pyramids. So the base, the capital B stands for the area of the base. So those little squares that are on the base of each of these little pyramids that we made. Okay, so if you add them all together, he says that's the surface area of the sphere. And we learned about that last lesson, right? With the video with all the oranges. Okay, so now he's going to put in that formula that we know from last lesson for surface area of the sphere, because that's going to be the sum of all those bases of all of those pyramids. Okay, so see, there's that formula from last time. 4 pi r squared is the surface area of a sphere. Okay, if you multiply the 4 times the 1/3, that's where he's getting the 4/3. Okay, and then here r to the second power times r is r to the third power, right? Because it's r times r times r. So that's that. Okay, pretty cool. If that made no sense, don't worry about it. Just use the formula, okay? That formula comes from calculus. Whenever we have that dot 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 and we're thinking about how many of those little squares and how many of those pyramids we could make, that's an idea of infinity. And calculus is all about infinity, okay? Because we could make those squares as big or as small as we wanted to. And the smaller we make them, the closer we would get to that curvature. All right, so let's use this formula. 4/3 pi r cubed for the volume. And anytime we have more than one thing going on, here we have multiplication and we have an exponent, we're going to be thinking about the order of operations. All right, and so for this one, whenever they label a number like right over the center, this is the diameter. Okay, and so just remember that if you're given the diameter, this formula requires that we know the radius. So you're just going to divide that by 2. 21 divided by 2. And that will be 10.5. Okay, so I'm going to put 10.5 in for the radius. And then I'm going to go ahead and put pi as, oh! Look at this, leave in terms of pi. I get to leave pi as a variable. This will be cool. Okay, let me show you what that means. So instead of using 3.14, what I'm going to do here is 4/3. Let me bring everything else down. My answer is going to have pi in it, and I'm just going to work around it like it were a variable like x or something. And so this is going to give me an exact answer, because I'm not going to be rounding pi to 3.14. 10.5 to the third power, I'm going to do in a calculator. Okay. 1157.625 is what I'm getting. There we go. Okay, and then this is going to be times pi and then also times 4/3. Okay, so I'm going to go ahead and write pi in front. Okay, multiplying, you can multiply in any order you want. And then times 4/3 times this. And this is what I'm going to do next. I'm going to multiply these two. Okay, so let me just hit times, and then I'll put in parentheses 4 divided by 3. I'm going to close my parentheses. Okay, ooh, look how pretty that is. I say it's pretty because it doesn't have a wacky decimal. Okay. I thought with the 4/3, 4/3 is 1 1/3, so I thought we might get like a 0.3 repeating or 0.6 repeating. Okay, and so that's my calculator part there. It's times pi, and if you look at the answer box here, they write the pi second, and that's fine. So in this box, I'm going to have, and this is not an actual problem of yours. This is just in the, I don't think this is, because it's on page 4 here. It's just an exercise. 1543.5 pi. So the final answer here is 1543.5 pi. And so we call that in terms of pi. This is all you have to enter in the box, but this is part of the number. Because then we're not getting those, we're not multiplying by an irrational number and getting a wacky chain of decimals, all right? Okay, let's do some problems that are in your work. All right, question 2. Will a sphere with a radius 50 inches or a sphere with diameter 100 inches have a greater volume, or will they be the same? Okay, so this one's a quick one. The volumes will be the same. The reason is that if the diameter is 100, the radius is 50. And guys, in the formula, 4/3 pi r cubed. Okay, all of this stuff is going to stay the same, okay, every time you do this for any sphere. The only thing that's going to change here is the radius. So same radius, same volume, okay? I wanted to just explain that a little bit because that's important. Same radius, same volume. Let's see, leave in terms of pi. This is another one where we want to leave the answer in terms of pi. I actually think these are a little easier. So volume equals pi r cubed, and the radius here is 12. So for this one, all we have to do is cube the radius because we're not actually going to multiply by pi. We're going to leave it in our answer. So here I'll just do 12 to the third power, and that's not right. Was this the diameter? Oh, that's the diameter. Bad, Miss Saltstein. You guys, if the diameter is 12, that means the radius is 6. So this should have been 6 to the third power. 6 to the power of 3. Whoops. There we go. 216. Let's see if that's what I was supposed to get. Nope. See, I'm getting 216 pi, and they're saying that's wrong, and it should be 288. So I'm like, what? Diameter is 12. Half of 12 is 6, right? Did they get this wrong? Did Pearson get it wrong? 6 times 6 times 6 is 216. I think maybe they got that one wrong. I'll ask Miss Angel, see what she gets. Okay, let's do some word problems. So let's do this one first. Let's just do this one. This one's your quick check. I don't want this video to be too long. Okay, so it says, Kyrie created a sculpture by forming a hemisphere with a radius of 20 inches. Then removing a hemisphere with radius 15 inches from it. Calculate the volume of his sculpture. So this took me a little bit to think about. So a hemisphere is half of a sphere, right? So what they've done, this sculptor has like scooped out this hemisphere in the middle. Okay, so imagine like a ball of clay. You've cut it in half, and then you've scooped out the middle of it. Okay, that's what's going on here. So what we really need to do is the hemisphere that has the radius of 20, we're going to subtract the hemisphere that has the radius of 15. All right, so what's the formula for volume of a hemisphere? Well, I mean, if the sphere is 4/3 pi r cubed, we want half of that, divide by 2 or times a half. And so really what we want here is half of 4/3. Okay, like this. So that's the fraction work that would go into this. We can cross cancel here. And we can see that the hemisphere's volume is going to be 2/3 pi r cubed. Okay? All right. I'm going to keep this in terms of pi, and I'll show you why at the end. So let's just double check that, because I got that wrong in the last one. Let's double check that these are radii, and they are. Whew. Okay, so we've got 20 cubed here and 15 cubed here. So 2/3 times pi times 20 cubed minus 2/3 times pi times 15 cubed. So let's go ahead and find 20 cubed and 15 cubed. So 20 to the third power is 8,000, and then 15 to the third power is 3375. So 8,000, and then sorry, I forgot it already. 3375. 3,375. All right. So check this out. So can we say that they are both 2/3 pi? And just hold that aside for now. And we're going to subtract the coefficients, okay? And then it'll be some number times 2/3 pi. Let's do that. Go away, Miss Celestine. All right, so 8,000 minus this. Minus 3,375 is 4,625. 4,625. Okay. Times 2/3 times pi. Okay. Look, they have not left the answers in terms of pi, so I'm just gonna, and they don't have any fractions in the answers, so I'm just gonna take that number and I'm gonna multiply. Oh wait, did they tell me to use 3.14? Yes, they did. Look right here. Use 3.14 for pi. Okay, so I'm just gonna multiply by 2/3, which is 2 divided by 3. See how I put it in parentheses? And then times 3.14. Okay, and it looks like they rounded it. Let's see. Round your number to the nearest, oops, I thought that was a highlighter, and it wasn't. Round to the nearest whole number. Okay, let me go back and look at this. So the 6 here would round the 1 up to a 2. Okay, the nearest whole number is the 1. Okay, but with the 0.6, it's actually closer to the next one. So 9,682. 9,682 is exactly what I was supposed to get. Right there. Yay! All right, guys. Have fun with this. I think this is a fun formula. I think you're going to like it. You're going to be like, I love funny volume of a sphere. I love it.